my name is Snehal. I'm a lecturer in population health and applied statistics, and I split my time between perioperative medicine and sports and exercise medicine. And in addition to that, I'm an MRC fellow as well, and so I'm running a 5-year project looking at how we can keep people at optimal capability to do the physical tasks of daily living for as long as possible. Just some background before I start is I wasn't sure what level to pitch this talk at, so there'll be a little bit of an element of, trust me, I'm a statistician, yeah, but trust me, I'm a statistician. And also to say that it's not based on any methodological work that I've done, it's based on the work that Tim Cole has done, and I've referenced his papers over here. Tim Cole's like an amazing statistician based at UCL, and everyone should read his papers because he's super cool. And also, just to give you an idea of time, this would be about 20 minutes, so there'll be plenty of time for questions and stuff like that. Yeah, okay. Also, by the way, this is the first time I'm talking to a group of people and just like staring at slides on my screen, so hopefully it's not too awkward. Right, so let's pretend we wanted to find out the relationship between TV viewing and triglyceride levels. Now, just to say from the get-go, this paper that I'm referencing here doesn't actually ask the question, what is the relationship between TV viewing and triglycerides? I'm just using this question to draw out an example of what I want to talk to you today about. So, say we go out on Tottenham Court Road and we find a bunch of women who are all 45 years old. We find 3,700 of them, and we ask them how much TV do they watch a day. And 15% say they watch less than 1 hour a day, 35% say they watch 1 to 2 hours a day, and about 20% say they watch 3 hours a day, more than 3 hours a day. Great. And then these 45-year-old women, all 3,700 of them, give us some blood, and we send it off to the lab, and we get their triglyceride levels measured. And this is the distribution of their triglyceride levels. And all I've done is overlaid a normal distribution on top of it. And you can see that the triglycerides in these women are right skewed, and that's perfectly normal. But if we wanted to find out what is the relationship between TV viewing and triglycerides, so TV viewing being your exposure of interest and triglycerides being your outcome, how would you analyze this? So the first thing is, well, can you just ignore the skewness of triglycerides and fit a normal regression model? And to be honest, you can't do that. You could fit whatever model you want, but whether the model you fit is meaningful or not is a different question. So in the first instance, let's just fit a regression model with triglycerides as our outcome, ignoring the skewness, and TV viewing as a categorical variable. And this is what comes out of this data. So just to talk you through what you're looking at here, this is saying compared to the group that watches less than 1 hour of TV a day, the group that watches 1 to 2 hours of TV a day has 0.13 millimoles per liter higher triglycerides than the group that watches 0 to 1 hour a day. The group that watches 2 to 3 hours a day has 0.23 millimoles per liter higher triglycerides than the group that watches 0 to 1 hour a day. And the group that watches 3 hours a day has 0.36 millimoles per liter higher triglycerides than the group that watches less than 1 hour a day. But in this regression model, we've ignored the skewness of the triglycerides. And so the question is, well, great, I fitted a model, but are the results valid? And for the results to be valid, your residuals from your regression model need to be normally distributed. And what I've drawn here is, what have I drawn? A graph of the residuals in blue, and I've just overlaid a normal distribution on top of it. And you can see right away that, you know, my blue graph and my red graph aren't very nicely aligned. So my residuals aren't normally distributed. And these results are really not very valid at all. And I think we can do better. So then going back here to the distribution of triglycerides in women, I've done every single transformation possible on triglycerides. So I've done the cubic, the square, the identity transformation, that's identical. So this graph here is the same as this, yeah? And what we're doing here is we're trying to make our outcome variable more normally distributed. Because if you make your outcome variable more normally distributed, you increase the chance that your residuals are going to be normally distributed, okay? So your square root transformation here, that looks quite nice and normal. But actually, I'll be honest with you, a square root transformation is a complete pain to interpret, so we're not going to do that. So let's focus on the log distribution. The log distribution doesn't look too bad, does it? I mean, there's a little bit of pointiness up there, but all in all, it's quite normally distributed. So let's log our triglycerides and do a regression, and let's try and see if we can interpret the regression coefficients, okay? So here, I've just logged my triglycerides and I've regressed it on a categorical variable of TV viewing. And these are the coefficients. So before we go on to trying to understand what these coefficients mean, it's probably worth just trying to see if our results are valid. So here's the graph of the residuals from my new regression and the normal distribution. And you can see that they're nice, and you know, the two graphs line up. So the residuals are normally distributed. So the coefficients you're probably going to get valid results from the regression model you fitted. Are there any questions before I continue, by the way? Okay, I'll take that as a no. Great.
Could you maybe just give a brief explanation what you mean by residual?
Oh, right. Sorry. So a residual. What I mean by residual is, so you have your triglyceride level measured for every woman, and then when you do a regression model, you get a predicted triglyceride level depending on your coefficients. Yes. So you have a predicted triglyceride level, and then the residual is just the difference between the two. It's the difference between what you've actually observed minus the fitted value from your model. Yeah, and so here all I've done is I've plotted the difference between the observed and expected values in the blue, and I've just overlaid a normal distribution with a mean of 0 and a standard deviation of 1 on top of it. Okay, cool.
Great, thank you.
Great. So what am I doing here? Right, so the regression results, what do they mean? So all I've done here is taken the regression from the previous slide. Yeah, so it's exactly this. I've just made it smaller, and I've just written out the formula. So to explain what that means is I have log triglycerides, and then 0.19 is the constant. 0.17 is the indicator for people who watch TV 1 to 2 hours a day. 0.15 is the indicator for people who watch 2 to 3 hours of TV a day, and 0.21 is the indicator for those who watch 3 hours of TV a day. Great. So what do these results mean? So the best way to explain that then is with a solid example. So say you wanted to know what is the mean difference in triglycerides comparing the group that watches 3 hours of TV a day versus 0 to 1 hour of TV a day. So if you look over here, there we go. The group that watches 3 hours of TV a day, their log triglycerides is going to be 0.19, which is the constant. That is 0, and this indicator variable is 1. So it's going to be 0.19 plus 0.21. And then likewise, the group that watches 0 to 1 hour of TV a day, their log triglycerides is going to be 0.19, because that is going to be 0, that is going to be 0, and that is going to be 0. Okay? Now, if we look at the difference between the log triglycerides of the group that watches 3 hours of TV a day and less than 1 hour of TV a day, it's 0.19 plus 0.21 minus 0.19, which is just 0.21, yeah? So then a nice property of logs, okay, is when you look at the difference between two logs is equal to the log of the ratio. So log triglycerides 3 hours a day minus log triglycerides less than 1 hour a day is equal to log of the ratio. which is equal to 0.21. And then all you have to do is exponentiate that and move things on either side of the equal sign. And you can say that compared to the group that watches 0 to 1 hour of TV a day, the group that watches 3 hours of TV a day, their triglycerides are higher by 1.23 times. Yeah? So the group that watches 3 hours of TV a day, their triglycerides are 1.23 times higher than the group that watches less than 1 hour of TV a day. And that's how we normally interpret logged regression results. Yeah, we exponentiate them. And that's fine, there's nothing wrong with that. But wouldn't it be really nice if we could just look at these coefficients over here and be like, ah, I know what those mean. Wouldn't it be great? I think we can do better than having to think, oh my God, what is the log exponential of 0.06? Because I don't know what that is. Off the top of my head, I have to go find my calculator. So we can get an easy interpretation. And in order to get an easy interpretation, that's where Sympercents come in. But before we talk about Sympercents, we need to understand what a percentage difference is. Okay? Right. 1 second. I need some water. Okay. So, percentage differences, there are a couple properties of percentage differences that make them a little bit, well, annoying actually. So first of all, percentage differences, they're not symmetric. So for example, if you think of the mean height of an average 20-year-old man is, the mean height of 20-year-old men, sorry, is 177 centimeters. And the mean height of 20-year-old woman is 163 centimeters. So women are 7.7% shorter than men. And the way you calculate that is you do 100 times the difference between men and women divided by the height of men. And men are 8.4% taller than women. And the way you calculate that is 100 times the difference between men and women divided by the average height of women. Yeah? And this is a little bit annoying because the difference between men and women is 13.7. Yeah, so on average, men are 13.7 times taller, centimeters taller than women, and women are 13.7 centimeters shorter than men. But the percentage difference is not the same. It's not symmetric. And that's one property of percentage differences that's a little bit annoying. So if someone asks you, what is the percent difference in height between men and women? I mean, you don't know. Do you say it's 7.7 centimeters or 8.4 centimeters? Yeah, it depends on what you're comparing it to, where you're starting from. The other problem with the percentage differences is that it's not additive. So for example, if you had a preterm infant, their weight increased by 10% each week for 2 weeks. At the end of the 2 weeks, how much has the weight increased by? Is it 20%? Or is it 1.1 for the first week multiplied by another 1.1 for the next week? So that being then 21%. The answer, by the way, is 21% because percentage differences are not additive. And then, you know, another example is if her weight increased by 10% in the first week and then fell by 10% in the second week, would she be back at her starting weight? Again, the answer is no, because percent differences are not additive. She'd actually be at 99% of her starting weight because at the first week, you've increased your weight by 1.1 and then you've fallen by 10% of that, so you multiply that by 0.9. I mean, this is like stuff we learn in, I don't know, secondary school, primary school, in school, but it's just annoying. And Sympercents avoids problems of asymmetry and non-additivity, okay? And the way you use a Sympercent is by using the mean of the two numbers as the divisor. So going back to when we were talking about mean height for 20-year-old men and women, the mean height of men and women together is 170.45 centimeters. So the symmetric percentage difference between men and women is 100 multiplied by the difference between the men and women divided by the average of the men and women, which is 8.04%. So you can say then, on average, men are 8.04% taller than women, and women are 8.04% shorter than men. Now, this is where I want you to kind of just trust me, I'm a statistician, because this calculation here is almost identical to this here, where it's 100% multiplied by the log of the difference between men and women, okay? I know I'm not going to get into why, but I just need you to trust me that the log of the difference between two numbers is approximately equal to the difference divided by the mean, okay? So, like, that's great and everything, and you're probably thinking, well, what does this have to do with anything? Yeah, and what it has to do with anything is that regression analyses with log transformed outcomes are so much easier to report when you think about 100 multiplied by the log coefficient than back transforming. Because when you back transform, you have to think about what the exponential is. When you do the 100 times log translation, you don't have to do that, and it's just much easier. I can give you an example of that now. So just to recall, this is the regression we did. We were happy that the results that we have produced are valid, and we said that compared to the group that watches 0 to 1 hour of TV a day, the group that watches 3 hours of TV a day, their triglycerides are 1.23 times higher. Okay, but here's an idea for an easy interpretation. And again, right at the top here, all I've done is rewrite the exact same equation. I've not done anything different. But now I'm asking, what is the percent mean difference in triglycerides comparing the 3 hour a day group to the 1 hour a day group? And the answer to that is to look at the triglyceride levels in the 3 hour a day group, the log triglyceride levels, sorry. And that's 0.19 plus 0.21, and you minus the log triglyceride levels of the 0 to 1 hour a day group, which is 0.21. Oh, sorry, that should be there from the beginning. And then where am I? Yeah, and so then you just multiply that by 100%, and you can easily say that the mean percentage difference in triglycerides between the 3 hour a day group and the 1 hour a day group is 21%. And just to reinforce this idea now, here on the top, I've given you the regression that we did originally. So this is regressing the log triglycerides on TV viewing, and these are the coefficients we got. And at the bottom here, I've done the regression of the log triglycerides multiplied by 100 on TV viewing, and these are the coefficients. The first thing to notice is that the coefficients are basically identical, except at the bottom, they're multiplied up by 100. Yeah, but it's the interpretation that's different. Because when I was doing this regression at the top, I was saying that the mean triglycerides is 1.23 times higher in the group that watches 3 hours of TV a day compared to the group that watches less than 1 hour a day. And likewise, if I flipped it around, I would be saying that the mean triglycerides is 0.81 times lower in the group that watches 0 to 1 hour a day versus the group that watches 3+ hours a day. Okay? And to do this, I needed a calculator because, well, I don't know how to exponentiate things in my brain. But over here at the bottom, the interpretation is very different, because I'm saying the mean percent difference in triglycerides comparing the 3 hour a day group to the 1 hour a day group is 21%. So on average, the people who watch 3 hours of TV a day, their triglycerides is 21% higher than the group that watches 0 to 1 hour a day. And likewise, if I flip it around, I can say on average, on average, the mean difference in triglycerides for those who watch 0 to 1 hour a day to 3 hours a day, their triglycerides is 21% lower. So that's what I mean. This is now symmetric. So just some important points if you're going to use this method in your work. The interpretation without back transforming, it only works on the natural log scale. So you have to use log to the base e. You can't do log to the base 10 or anything like that. It has to be to the base e. And so it'll work with any positive valued continuous outcome data, which I think is most of the stuff that you'll probably use. Yes? Yeah, okay. In the methods, you're going to have to write something along the lines of 100 times the log differences. They're interpreted as symmetric percentage differences, and you'd have to give the references that I gave at the beginning. And just to reinforce some points is that some of the advantages of this method is that it's a simple interpretation of a common transformation. So, you know, I was just able to look at those results and tell you what it means without having to think about what the exponential is. And everyone does a log transformation. I mean, any skewed data, the first thing people try and do is log it. And something that I think is actually not necessarily appreciated well enough is that you're able to compare outcomes that are measured on different scales with this transformation. So going back to the question I asked, what is the relationship between TV viewing and triglycerides? That's not actually the full question that we asked in the paper, because we asked what is the relationship between different types of sitting and a whole host of biomarkers for cardiovascular disease and diabetes. And right away, you can see, can you see? Yeah. I've put, by doing this log multiplied by 100 transformation, I'm able to put diastolic blood pressure, systolic blood pressure, cholesterol, triglycerides, fibrinogen, CRP, HbA1c, all on the same scale. And so I can see, just by looking at it, television viewing is more strongly, I mean, roughly speaking, more strongly associated with triglycerides than it is with, for example, HbA1c or systolic blood pressure, even though they're measured on completely different scales. Because now I've made the outcomes, all of these outcomes, on a similar scale of percentage increase. And like that now. Yep, that's it. If you have any questions, now it's time to ask me. I hope you'll heard me for the whole thing. Yeah, if you have any feedback, any other things you'll want me to talk about in the future, just get in touch.